Questions? All right. So we did an object rolling down incline last time. Talked conceptually about the energy distribution. That objects sliding or rolling, if they have the same mass, they have the same gravitational potential energy, but if it's going to roll, some of that energy has to go into getting it to roll. And the higher the coefficient of the moment of inertia, the more energy has to go into rotating it, which means less for the translational motion. Oh, and by the way, when we started chapter 9, talked about linear / translational motion. Actually have come across someone who used the term translational motion. If you watch BattleBots, they talk about if you cannot show you have translational motion, you'll be counted out. It'll be a knockout. Of course, they also talk about angular speed, like 100 miles per hour. Okay, no, that's what they really mean is the tip speed, not the actual angular speed. We'll just start out with a plain old, that part, plain old disk here. And we'll make that 5 kilograms. We'll make that 4 kilograms. And assume ideal group. And what I want to know is the acceleration of masses. So we're going to start out with that, and then we'll throw in some chapter 9 stuff. So this is a chapter 4 or 5 problem. And we'll just start out with force diagram. Do assume that something is holding the pulley up. That's the 5, and that is the 4. All right, what are the forces?
Weight
Acting
on the 5 kilogram box, 4 kilogram box, and is it ideal? Other up is ideal. Coast.
Wait, what was that last bit?
Wait.
You said weights acting on 4 and 5.
Yes.
Which
Down.
way? Yeah, okay, that's the part I was waiting for.
Mothball. Then up on the ground.
Ideal rope. So it has no weight. All right, so there's the weight. What else?
Tension.
Okay, acting which way on what?
The box and the ropes towards each other.
Okay. So I have a tension here, I have a tension here, I have a tension here, I have a tension here. What else?
Would there be friction on the pulley in the rope?
Ideal.
Oh, just kidding.
Nothing else.
As far as the problem is concerned, we don't need anything else. However, there is one other force we have to discuss that will be acting on the rope.
Normal force touching the circle for the pulley.
Yeah. So which way is it acting on the rope?
Up on the rope.
Yeah.
And down on the pulley.
And just, we could imagine that. And since that's the only normal force, we'll just leave it like that. So again, this is just a chapter 4 problem. Equations of motion, or, oh, let's do it right. In which direction will the 5 kilogram mass move or accelerate?
Down.
And 4?
Up.
I would hope so. Coordinate system, or coordinate axes, or axis. What do you want to make the positive direction here?
Same as acceleration.
Okay. So we'll make that positive direction. And what about here? Same answer? Decomposition, do we need to break anything up? All right, equations of motion. We'll have 2 equations of motion. What are they? Come on, let's dazzle all the international fans. Give me an equation of motion that is, let's say, a 5 kilogram mass. What is the equation of motion?
Weight minus tension is equal to
Equals what?
MA.
All right, like that?
Yes. Because we're not including that normal force, correct?
Correct. There's no normal force acting on the 5 kilogram mass, so. All right, let's do the other one.
Tension minus weight equals MA.
So if I add those 2 equations, I get acceleration equals 0. That doesn't seem right, doesn't feel right. What's wrong with these equations?
The acceleration needs to be down on 4.
I think so, yeah.
I mean, like the negative, I guess.
No, not a problem with the negative. The acceleration, we knew the direction of acceleration. We know that if this accelerates down, that's gonna accelerate up, and we chose those to be the positive directions, so we're good as far as the signs go. There's a rookie mistake in there.
It's not weight sub 5, weight sub 4, because it's assuming that they're the same weight in those equations.
I see. Yeah, the subscripts are missing. That's 5, that's 4, that's 5, that's 4. The accelerations are the same. It's an ideal rope. It's not stretching or anything like that, so they will accelerate at the same rate. Scalar acceleration. All right, now we add them. The tensions will cancel out, and I'm left with weight 5 minus weight 4 is equal to M5A plus M4A. That's an M, which is M5 plus M4 times A. And over here, I didn't substitute immediately, so we'll substitute now. And sorry to spoil that by not just asking. And so we end up with acceleration equals M5 minus M4 G divided by M5 plus M4. And we'll put this on Earth. So this becomes 1 times 9.8 over 9. units.
Meters per second? Per second square.
Yeah, I heard somebody whispering over there. Acceleration squared. All right. Questions on this problem? Because we're about to add a twist to it. About to make it a chapter 9 problem. Then let's make it a chapter 9 problem. We're going to remove one of our ideals. There is now friction between the rope and the pulley. As a matter of fact, the friction between the rope and the pulley is static friction, which means that the rope is not going to slide across the pulley, but it will move. There's not going to be any slipping at all. There exists friction, static friction between rope and pulley. Now, that is going to change our tensions. The fact that the tension is now no longer the same on both sides. Be like having, if we turn that into a linear problem, it'd be like having a tug of war, two sides evenly matched. Somebody comes into the middle and starts pulling in one direction, then the tension that they're experiencing is not necessarily the tension that they're experiencing. So we now have to bring the pulley into it. So this is FT5, FT4. Now we are still assuming a massless rope, but we will have a tension acting at the other end here, FT4, FT4. FT5, FT5. If the rope had weight to it, then these tensions would not be the same anymore. But that's for another day or another class. This does complicate the math slightly complicates it. And since the pulley, it now has friction, the pulley also has mass, so assuming ideal pulley, the fact that the pulley has mass, so this now has mass, and then static friction. Because we are dealing with a rotational motion chapter, so therefore rotational motion has to come in here somewhere. Yeah.
Are you about to put the friction on the pulley right now?
Is that to actually put the weight on the pulley?
Okay.
So we have weight acting down this way. We have a normal force acting down here. So this would be weight pulley. I'm going to call this Y rope. And then there's a normal force pulley there. Now the friction on the rope, there is friction acting, let's see, so if it were frictionless, it would be spinning going like that. The rope would be going like this. And so friction opposes that, so friction would be acting in this direction. And then this way on the pulley. We could simplify this just a little bit. If we assume that the pulley here So we have pulley and rope. If I just treat this as I have this bit of rope right here, this bit of rope right here, and then where the pulley and the rope are touching, I consider that just one object. That way the friction becomes an internal force and I don't have to worry about it. So I'm going to change my drawing here. And so the part of the rope that's touching the pulley, I'm just going to consider that with the pulley as one object. It reduces it down to just 3 equations. We could do more, but 3 crucial equations. All right, so first, what's the equation of motion for the 5 kilogram mass? Let's back up for just a second. What is the direction of the acceleration of the 5 kilogram mass? And the 4 kilogram mass? And the pulley?
Counterclockwise.
And what direction would that be?
To the left.
To the left.
Wow.
Sorry. Done the wheel thing, haven't I? What's the direction of the angular velocity?
Clockwise.
I would have said counterclockwise.
Is it like to the middle?
Oh, well, if it's you, like from your point of view, it's counterclockwise.
So how do we resolve that?
We decide which one it is, just pick one.
No.
We define a direction.
It's towards the center, right?
Towards the center
Towards the center?
of the wheel?
Yeah.
There'd be some centripetal acceleration for any part along here, but that's not sufficient. If I needed to describe which way this is spinning, I need to come up with some system that will make it clear that if I told Miss Sasson, and she's not in here to see it, I need to say it as efficiently as possible. So if I said, well, if you're standing in the middle of the room looking towards the board, it's going clockwise, that's just a lot of words. We need to do something better than that. So, the powers that be decided upon a right-hand rule. You're saying I did not do this part, or you just forgot this part?
I don't think
You didn't spin it yet.
So what you do is, there's obviously an axle here. So, right hand, it's not dominant hand for the left-handed people. It's the right hand, your thumb sticks out from the other fingers, and it is going to be basically pointing along the direction of the axle, which means it's either pointing that way or that way. You want your fingers to curl in the direction that the wheel is spinning. So if the wheel is spinning around like that, so I want my fingers to curl in that direction, my thumb points it along the axis towards the front of the board. That is the direction of the angular velocity. There's nothing physically going towards the front center, towards the board, it's just the mathematical convention. So as this thing is spinning around like this, we would say that, then I could say to Ms. Sasson, the angular velocity is towards the board, and she will know it's spinning like this. If it's spinning like that, what is the direction of the angular velocity?
Away from the board.
Yeah, and you could also check that by doing this. If I'm spinning like that, what is the direction of the angular velocity?
Away from the board.
Up.
It's either going to be up or down. You're going for up.
Yeah.
Why?
It's that way.
Yeah. So my thumb will either point up or down. The wheel is spinning around like that, up. So in the case of this, if I start at rest, and it is going to then go into having an angular velocity in that direction. Well, if I'm going from 0 to a velocity in that direction, my acceleration has to be in that direction. So I'm gonna have angular acceleration that way. So let's set up our coordinate system. I want I hat to the right, J hat up, and K hat comes out of the board. This is the right-handed coordinate system. I cross J is K. All right. So this is going to accelerate in the negative J hat direction. This will accelerate in the positive J hat direction. You can still get away with the pluses there. This will accelerate in the K direction. It's angular acceleration will be in the K direction. All right, so the equation of motion of the 5. It's all very similar to what we just did.
Wait, 5 minus tension 5? Equals like 5A.
All right. What about for the 4 kilogram mass?
FT4 minus weight 4 is equal to M4A.
Minus weight 4 equals 4. All right, and now for the rotating